Species are continuously confronted with a changing environment, largely caused by anthropogenic or human effects and climate change. And if we're going to be able to mitigate these changes, one of the key questions we have to be able to answer is whether the organisms confronted with these changing environment can adapt quickly enough. If they can't adapt quickly enough, what is it that limits their capacity to adapt? And if they do or don't adapt, what are the consequences for the wider community and the ecosystem as a whole? So my name is Stewart Plaistow, and I'm the lead investigator on a NERC highlight grant trying to look at some of these questions by doing large-scale experiments on a small crustacean called a water flea that has important consequences for freshwater ecosystems and the ecosystem services that they provide. So shallow freshwater ecosystems are particularly pertinent for looking at questions to do with climate change and rapid adaptation. Shallow freshwaters cover something like 3% of the global surface of the planet. And because they have such a high surface area to volume ratio, they're particularly vulnerable to climate change because they heat up quickly. So they're very susceptible to things like heat waves. And on top of that, in most cases, if the climate changes and the organisms that live there can't cope, they normally would distribute to somewhere else. But often in shallow fresh waters, these are bodies of waters that are actually bounded, so the organisms can't disperse. So in that case, they really have to be able to adapt or face extinction. So in order to understand what limits the ability of a species to adapt to these rapid environmental changes, we need to be able to manipulate the evolutionary potential of populations. So we need to be able to tease apart genetic diversity and these measures of phenotypic plasticity. And because we work on a clonal organism, we can do that quite easily in large-scale ponds, such as the one we have here at the Liverpool Brian Moss Mesocosm Facility. So by setting up the same ecosystems, but when we put in the particular species we're interested in, Daphnia magna, we can either put in a single clone, so no genetic diversity, or 6 clones or 43 clones, so you have a high genetic diversity. And the clones that we put in, they can either be plastic clones that we've measured their response to changes in environments in the lab, or they can be clones that are less plastic. So if each pond has a different makeup of genetic diversity and clones that are plastic or not, we're able to tease apart the relative effect of those two things playing out in semi-natural ecosystems. So I've explained how we manipulate the evolutionary potential of the water fleas that go in our ponds or mesocosms, but the next thing we need to be able to do is to manipulate the environment that they experience. And in this case, we're interested in heat waves. So what we've built here at the University of Liverpool Mesocosm Facility are ponds or mesocosms in which we can completely program and control the thermal profile of the ponds. So we're able to make individual ponds either have a heat wave or not. And we've been using this in this experiment to understand how different populations with manipulated evolutionary potential respond to having a heat wave every year instead of every once in a blue moon. So we've manipulated the evolutionary potential in different ways in all of our mesocosms, and we've manipulated the frequency with which each of those mesocosms has a heat wave or experiences a heat wave. And we've been running that experiment for the past 3 years or so, and every few months we've been recording samples to track the evolution of the Daphnia themselves in each pond, both the phenotype and the genetic evolution. We've been taking samples to look at the effect on community dynamics and taking water samples to look at the broader effects on water chemistry. And we're currently at a stage now where we're processing all that data, and we should soon be at the point where we can tell you what is more important in terms of adapting to an increased frequency of heat waves? Is it genetic diversity or is it phenotypic plasticity?